Here's a situation you'll encounter when building real streaming pipelines. You need to process each chunk, but the processing involves an asynchronous operation, a database lookup, an HTTP request, a file read. How do you ensure chunks are processed one at a time, in order, without letting the next chunk arrive before you're ready for it? The answer is the _transform callback protocol, and it's more powerful than it first appears. When you implement a transform stream, you call the callback function when you're done processing a chunk. Until that callback is called, the stream infrastructure does not deliver the next chunk. It waits. This is automatic sequential execution built into the stream itself. So if your _transform method makes an async database call, you simply don't call callback until the database responds. The chunk that produced the query is processed. The response gets pushed downstream. Only then does the next chunk arrive. No matter how many chunks are waiting, they queue up and process one by one. This pattern solves the classic async loop problem cleanly. You don't need to manage a queue manually. You don't need to track which async operations are in flight. The stream's own backpressure mechanism enforces serialization. The book demonstrates this with a URL checker, a stream that reads URLs, makes an HTTP request for each, and outputs the status code. Because each HTTP request is awaited inside _transform before the callback fires, each URL is checked one after the other, in order. This is sequential execution through streams, elegant, automatic, and correct. But sequential isn't always what you want. Sometimes you want speed, and that means parallelism, which comes with its own complexity. Sequential processing is correct, but it can be slow. If each URL check takes 200 milliseconds and you have 1000 URLs, that's more than 3 minutes, even though your CPU is idle for most of it. The opportunity is obvious: process multiple URLs at the same time. Launch several HTTP requests in parallel, collect results as they arrive. This is unordered parallel execution. You process chunks concurrently, and results come back in whatever order the async operations complete. The implementation is a custom transform stream where you don't wait for the async operation to complete before calling the callback. Instead, you call callback immediately after launching the async work, allowing the next chunk to be delivered right away. When the async operation completes, you push the result directly. There's a subtlety here: you need to tell the stream when all in-flight operations have finished. You do this by tracking active task count and overriding _flush, which is called once the input stream ends. Only when all pending operations complete do you call the _flush callback, signaling that the stream is truly done. The book builds a URL status monitoring application using this pattern. Rather than checking each URL sequentially, the stream launches up to n concurrent checks and pushes results as they arrive. The order of results may not match the order of inputs. If URL number 3 responds faster than URL number 1, number 3 appears in the output first. For many use cases, order doesn't matter. If you're gathering metrics, counting successes and failures, or writing results to independent files, unordered parallel execution gives you all the speed with no coordination overhead. But sometimes order matters. When it does, you need a different approach. Unordered parallel execution is fast, but unconstrained parallelism is dangerous. If you launch 10,000 HTTP requests simultaneously, you overwhelm the remote server, exhaust your file descriptor limits, and potentially crash your own process. You need a concurrency limit. Limited parallel execution adds one constraint: at most n operations run at a time. The mechanism works like this. You maintain a counter of active operations. When a new chunk arrives, if the counter is below the limit, you launch the operation immediately and increment the counter. If the counter is at the limit, you queue the chunk. When any operation completes, you decrement the counter and check the queue. If there's work waiting, you pull the next chunk and start processing it. This pattern is equivalent to a worker pool or a semaphore. The stream machinery handles delivery of new chunks, and your concurrency controller decides when to actually process them. The book implements this as a reusable class, a parallel stream with a configurable concurrency limit. You instantiate it with the desired concurrency and pass in the async processing function. The class handles all the bookkeeping. In practice, the right concurrency limit depends on your bottleneck. If you're making HTTP requests to an external API, the limit might be 5 or 10 to stay within rate limits. If you're doing CPU-heavy work, the limit should equal your number of CPU cores. If you're doing file I/O, the sweet spot depends on your storage system. The key insight: controlled parallelism gives you most of the throughput benefit of full parallelism while protecting both your system and external dependencies from being overwhelmed. It's the professional's version of just do everything at once. Next, the hardest variant: parallel execution that must preserve order. Here's the hardest stream challenge: You want to process chunks in parallel for speed, but you need the output to come out in the same order as the input. If chunk number 3 finishes before chunk number 1, you can't push chunk number 3 downstream until chunk number 1 is ready. This requires a buffer and a sequencing mechanism. The idea is straightforward even if the implementation takes care. Assign each chunk a sequence number. Launch all async operations concurrently. As results arrive, store them in a buffer indexed by sequence number. Before pushing any result, check if the next expected sequence number is available in the buffer. If it is, push it and advance the counter. If it isn't, wait. Consider 5 chunks processing in parallel. Chunks 2, 3, and 4 finish quickly. Chunk 1 is still running. We buffer results for 2, 3, and 4. When chunk 1 finally finishes, we push 1, then immediately flush 2, 3, and 4 from the buffer in order. The worst case is when the first chunk is always slowest, you end up holding N1 results in the buffer waiting for position 0. But in practice, most async operations have similar latency, and the buffer stays small. The book's implementation uses a reusable pattern. Each chunk gets an index, results are stored in a results array, and after each completion you scan from the current output position forward, pushing consecutive completed results until you hit a gap. When would you use this? Anytime you're transforming data that must remain in order, streaming compression followed by in-order writing to disk, processing CSV rows where row numbers matter, or any pipeline where downstream consumers depend on sequence. Together, sequential, unordered parallel, limited parallel, and ordered parallel cover the full spectrum of async control flow through streams.